Okay, so what we've been able to find mathematically is from the titration sketched on the right-hand side, and given the pKa of 4.76 for that acid, we've been able to find that before we added any sodium hydroxide, the pH was 2.55. So that's our initial pH. What's happening though is a reaction with sodium hydroxide. So this is just like the titrations you did last year. And so what we had was ethanoic acid, and last year it was probably vinegar for your titration, was reacting with sodium hydroxide and neutralizing. To make that. So that was going to be present in solution. The thing is that these two here can both dissociate. They're both present before we get to the equivalence point. This reaction shows equivalence point. They're both present before I've added enough of this, so they are able to create what's called a buffer solution. And so everywhere from here to what we call the equivalence point volume, there will be a buffering effect happening. Okay? What we need to do is say, okay, at what volume is this equation true? At what volume is it? And for that we need to use that MCV relationship. I've made things really simple. I've made the concentration of both of these solutions identical. This will not always be the case. So I'm going to show you the mathematics behind it, and then we'll go back. All right? So, I like putting N at the top because the numbers in front of these things, which in this case is 1, but the numbers in front show the mole ratio. So if it was 1 to 2, I know that's a 1 to 2 ratio for N. So N, C, and V. I'm going to use my volume as mils, but milliliters, because, sorry, I've taken it away here, but in my original sketch, my volume of sodium hydroxide will be in mils, so I might as well just pretend that it's litres and then go back to it being mils. You'll see what I mean. So, I know the concentration of this, and I know the volume of this is 20 mils. So I write 20 over 1,000 so that I'm not having to convert. It's 20. All right, that's the number that I can see there. Therefore, I can find the amount of that. N equals C times V. So that becomes 9. And then I'm just going to go over 1,000 because it's easier. 9 thousandths. These are in a 1-to-1 ratio. So this is 9 over 1,000. I also know this value here. And so to find volume, I go and I rearrange my N equals C over V. Sorry, C equals N over V. Okay, I'm trying to find volume, so it's N over C. That divided by that equals that. Not surprisingly, because these are the same concentration, 1-to-1 ratio, I get 20 mils. Okay, so I'm going to do a dashed line at 20 mils. And because I'm sketching, I can draw it anywhere I want. Just don't go too far to the left, because it'll look stupid. So we come quite far to the right, at least halfway. So here's my 20 mils, where this reaction is correct. Now I've got that 20 mils, I also need to identify a thing called the half equivalence point, because this is where the concentration of the acid and its conjugate base will be identical, exactly the same. And we know from our previous stuff on buffers, that means pH equals pKa. So I've got another point on my graph that I can use, which is fantastic. Another point that I can actually help with my sketch. Well, half of 20 is my half equivalence point. If this number was 40, it would be 20. If this number was 15, it would be 7.5. So I'm just halving the volume that I've calculated using my level 2 NCV relationship stuff. So I now go halfway. Oh, that's about right. We're sketching. Don't be too worried about it. And I'm going to put 10.0 there. And I'm going to do a dashed line, not too high this time. Because it's, well, maybe a little higher than that, but not as high as that one. Because it's all going to be down here somewhere. Alright? Now, knowing that relationship and knowing that it's 4.76, I'm going to do a dashed line here. And I'm going to say that that's at 4.76. Where those two meet is my next point of my graph that I know. Now, here's the trick. It's not just a straight line. Oh, look, yay. What happens is as soon as I add some sodium hydroxide, this increases dramatically as the hydronium ions are starting to be used up a bit. And I showed that in the last video. Then when it gets up to about 3.76, so one below this, it starts only changing very, very slowly until it gets very close to this, and then it dramatically shoots up. I'm going to have to stop there because I don't know what it's going to shoot up to yet. Okay, so by knowing some stuff from last year, looking at our balanced equation at equivalence point, we can find the equivalence point volume. Once I've got that, I can find the half equivalence point volume, and knowing the relationship between pKa and pH when these two are in the same concentration, I can mark a new point on it. Then by knowing my general shape, that it suddenly goes up, then slows down a bit, and then suddenly goes up at the end, then I can sketch in the first part of my graph. All right. Any questions on that before I stop there?